Let's take a moment to look at limits of trig functions here. So here's the logic here. I'm not going to prove anything or whatever, but let's start by finding the limit of sine of x as x approaches 3x, or as x approaches pi over 3. And what I'm going to do is draw a graph here to kind of help show you the logic of what's going on. So here's 2 pi, negative 2 pi, and this would be pi, pi over 2, 3 pi over 2, right? Okay. And maybe 1, negative 1. And then the sign starts here, goes up, down. Okay, now in section 2.5, we're going to learn about continuous functions, functions that are continuous. And the intuitive idea of continuous functions, I'm going to write this down here, continuous functions. The intuitive idea is that a continuous function forms an unbroken graph. Okay, there's no holes in it, there's no breaks where they're separated. It's kind of like if you had your pencil and you were drawing it, you could draw the whole graph without ever having to lift your pencil up off of the paper. And certainly the sine of x is continuous. I could keep doing it without ever lifting my pencil off the paper. And when a function is continuous, it has the property that the limit as x approaches c of f of x is equal to f of c. So what it means is, as you approach a certain point, right, as you approach c, the function actually approaches the value that the function is defined at c. And that actually captures this idea of continuity. We're going to learn more about that in the next set of videos here. But this is a really important concept, because what it means is if you know a function is continuous, then all you have to do to find the limit is plug c in to the function, right? Because the limit of f of x as x approaches c is just f of c. Okay, so the sine and cosine are excuse me, the sine and cosine are continuous, right? They're these continuous waves, and so if I want to find this limit, then I just have to plug in sine of pi over 3, and sine of pi over 3, let's think of our unit circle, it's this one, so the sine is the square root of 3 over 2, and voila. So pi over 3 is here, right? And as I approach pi over 3, I get square root of 3 over 2. Okay? And so it is approaching the value of the function at that point. So easy. Sine, cosine, no problem. Now tangent and secant and cosecant and cotangent, you do have those asymptotes where the function's not defined. So let me graph tangent here. So here's 2 pi. Here's pi. This is pi over 2, 3 pi over 2. Okay, and then this is negative 2 pi, negative pi, negative pi over 2, negative 3 pi over 2. And tangent has these vertical asymptotes whenever cosine is equal to 0. Okay, because tangent is sine over cosine, and when cosine is 0, you get a 0 in the denominator, and it's undefined. So this goes like this, right? And so you get this graph repeatedly. Every pi, you get that graph. Well, notice on like the interval from negative pi over 2 to pi over 2. So here I'm not including the pi over 2. These are all the points within the interval, but not the endpoints of the interval. Well, this function, tangent, is continuous on that open interval. It is continuous, just not at the endpoints, because at the endpoints the limit doesn't exist. Okay, and the function isn't defined there. Okay, but if you're inside the interval, the open interval, and you're not at one of those endpoints where you get the asymptote, it is continuous, and you could just plug it in, right? So pi over 4 is like right over here, right? And it would go up here, and we know that tangent of pi over 4 is 1. So within this interval, if your c is in this interval, then you can just evaluate the tangent at that point, right? Pi over 4. In this case, it's equal to 1. So you can take the limit there, no problem, okay? So now let's try this. Let's do the limit as secant of x. The limit as x approaches pi over 2 of secant of x. So let me do a graph of secant of x. And here's 2 pi, here's pi over 2, and 3 pi over 2. And then over here, this is negative 2 pi, negative pi over 2, and then negative 3 pi over 2. And then you got like negative 1 here. And so I'm not going to draw it, I'm just going to do a dotted line. This would be my cosine, right? My cosine wave. And then the secant, remember, is going to have a vertical asymptote. This is really 1 over cosine, and it'll have a vertical asymptote whenever the cosine crosses the axis. So you got one here, and here, and here, and here. And so then it'll go down and touch and go back up. This will go here, touch and go back up, like that. Okay, so this is the graph, not the dotted line is the graph of cosine, but this solid line is the graph of secant. And so, for example, if I go to the interval of the open interval, negative pi over 2 to pi over 2, okay, now if I go to, I can't include these endpoints because that's actually where the vertical asymptote is. But this open interval, for all the points inside the open interval, you got this continuous graph. It's going off to infinity, you know, but at any point inside the interval it has a finite value, right? So you have that continuous graph. So if the limit here is at a point inside the interval, you could evaluate it just like tangent. But in this case, you want to take the limit as x approaches pi over 2, and in that case it's going off into infinity. And so remember, those vertical asymptotes was one of the places where limits don't exist, and so this here, the limit does not exist. So D in E does not exist. Okay. So basically, sine, cosine, no problem. Tangents and cotangent, secant, cosecant. For a large majority, you can find the a limit. You just have to be careful of those asymptotes, right? Now, let me make a further point that any of the things we did to transform the graph, what it did, any of those things, it just shifted the graphs around and stretched them out. And so if I took this and shifted it around anywhere, stretched it out, I would still get a continuous wave. And these would still be continuous, except, you know, you would still have asymptotes. They just wouldn't be in, the asymptotes wouldn't be in the same place. Okay, so if you're changing these functions in such a way that we did when we graphed them and shifted the graph in different directions, then you can use these same rules, okay, because the graphs are still continuous and you can evaluate them. But if what you're doing is you're composing, like if I'm taking sine, and we looked at this, sine x 1 over x, if I'm putting another function inside, now this was not one of the things that we did when we graphed the functions, right? We didn't do this. That's what made it a little strange when we looked at it, when we talked about limits. And in fact, this thing would oscillate up and down infinitely as you got closer to 0, and so it never had a limit. It never stopped oscillating. Okay, so if it's one of the normal shifts that we did, you can use this. You can evaluate and find limits. But if it's something else, you want to be careful, okay, because the limit could be more complicated. But let's do one more example here, kind of combining everything we learned. If you notice, this is a pretty complicated function here, but what I have here on top are just horizontal shifts, a period change. I've changed the amplitude. This is the sort of changes we made when we graphed the functions, right? So there's no problem here. I can take the limit of that. And then look at the denominator. If I plug 3 in here, I get 9 minus 1, that's 8. And so I could take the limit of that too, because I don't get a 0 in here. So I can actually use the quotient rule and take a limit of the top and bottom. So limit as x approaches 3 of 20 cosine pi over 2x plus 30. And this would be limit as x approaches 3 of x squared minus 1, right? So I'm taking the limit of the top and bottom using the quotient rule. And you could break this apart and take the constant multiple out and then take the limit of this. But basically, if it's something that if it's a sine or a cosine, there's no asymptotes. And if it's just shifts that we did when we graphed them, no problem. I can evaluate that. Okay, so this will be 20 cosine pi over 2 times 3 plus 30 all over, and then I can evaluate this, 3 squared minus 1. And notice I could drop my limit here because now I've taken the limit. By evaluating them, I've taken the limit. So this is 20. Now this is 3 pi over 2. So cosine is equal to 3, when it's equal to 3 pi over 2, that the cosine is equal to 0. So this is 20 times 0 plus 30 all over 8 minus 1, or 9 minus 1, sorry. And so this is just 30 over 8, and then that would be 15 over 4. And that would be the limit of that. Okay, so you can do some pretty complicated functions in with these techniques, even involving the sine and the cosine. So keeping in mind this idea of continuous functions, and when these other 4, sine and cosine, are always continuous for the different transformations we did when we graphed, these do have those vertical asymptotes where the limit does not exist. Otherwise, the limit does exist, and you can evaluate those as well. So.